Welcome to part 2 of the wave lesson. Diffraction of waves. Diffraction of waves occurs when the waves are spread out when passing through a narrow gap. Diffraction can easily be seen when the size of the gap is less than the wavelength of the waves. Based on this figure, you can see that on the left, the obstacle is longer than the wavelength, so there is little diffraction. However, on the right, the opening in the obstacle is shorter than the wavelength, so there is a lot of diffraction. A summary of the wave characteristics before and after the diffraction is given within this table. Wavelength, frequency, and speed remains the same, however, the direction of motion changes as the wave spreads out, depending on the size of the obstacle. Diffraction of sound waves. Figure 1.25 shows a student walking around a corridor. When reaching the turn, he could listen to the music on the radio that was placed behind the turn. This is due to the diffraction of sound waves. Sound waves travel in a circular motion, and when passing through a turn, the wave can still travel to the other corridor. Diffraction of light. Figure 1.26 shows how diffraction of light works. A light source, commonly known as monochromatic light, passes through a very narrow slit and projected on a screen. The bright fringes show the light waves do not intersect each other, while the dark fringes shows there are intersections between the light waves. Interference of waves. Principle of superposition. In figure 1.27, wave A and wave B are traveling against each other. Both have the same amplitude, and the amplitude of the wave doubles, A plus B, when both waves interfered. After interference, both waves travel with the initial amplitude. This situation is called constructive interference. In figure 1.28, wave A and wave B are propagating into each other. Wave A has a positive amplitude, while wave B has a negative amplitude. During interference, the sum of the amplitude for the wave A plus B is 0. After interference, both waves propagate with initial amplitude. This is called destructive interference. Interference is the superposition of two waves that come from two coherent sources. Two waves are said to be coherent if the amplitude and the phase difference for both waves are identical. Figure 1.29 shows the interference of two coherent waves. The solid line shows the peak of the waves, while the dotted line shows the flow of the waves. The point where peak and peak or throw and throw intersect are called constructive interference. The line that passes through all constructive interference is antidodal line. The point where peaks and throws intersect are called destructive interference. The line that passes all destructive interference is a nodal line. This is the general equation to find wavelength. Lambda is equal to AX over D, where lambda is equal to wavelength. A is the gap of two coherent sources, X is the distance between two nodal or antinodal lines, and D is the distance between the coherent sources and distance between two nodal or antinodal lines. Based on this equation, we know that X will decrease when A increases, and X will increase when lambda increases. Water wave interference experiment. The hypothesis. The smaller the wavelength, the smaller the distance between the two consecutive antinodal or nodal lines. The aim: to observe the change in distance between two consecutive antinodal or nodal lines when wavelength is changed in the distance between two coherent sources and distance between the two nodal or antinodal lines is constant. These are the variables analyzed throughout the experiment. The manipulated variable is the wavelength. The responding variable is the distance between two consecutive antinodal or nodal lines. The constant variable is the distance between two wave sources, distance between the source and where x is measured. The apparatus for this experiment includes a ripple tank, a stroboscope, and a ruler. The procedure. Step 1. A ripple tank is set up. 2 spherical dippers are placed 5 cm apart and adjusted so that they touch the water surface at the same level. Step 2. The motor is started. Step 3. The interference pattern is observed using a stroboscope. Step 4. The value of x is observed for the different values of wavelengths, which is modified by the rheostat. These are the expected results of the experiment. From the results, the left figure shows that when we increase the wavelength, the distance between 2 consecutive antinodal or modal lines increases. Conversely, the right figure shows that when we decrease the wavelength, the distance between 2 consecutive antinodal or nodal lines increases. In conclusion, the smaller the wavelength, the smaller the distance between 2 consecutive and antinodal or nodal lines. Based on the lesson we've had so far, let's try to figure out this question. The figure shows a wavefront pattern in a ripple tank produced by a vibrating dipper at a frequency of 5 Hz. What is the wave speed? Please pause the video and try this yourself. Using the equation V is equal to F times lambda, we can find that lambda is equal to 1.5 centimeters. Question 2. A mechanical stroboscope has 12 slits and rotates at a frequency of 5 Hz. The stroboscope is used to observe water waves. The observer notes that there are 6 consecutive bright bands at a distance of 20 centimeters. Calculate the speed of the wave. Please pause the video and try this yourself. To use the equation V is equal to F lambda, we first need to find F and lambda. To find F, we multiply the number of slits 12 to 5 Hz, which gives us 60 Hz. To find lambda, we divide 20 by 5 to get 4 centimeters. Given this, we can find that 60 times 4 gives 240 centimeters per second, which is V. Let's move on to the next question. The diagram shows a full-scale interference pattern of a ripple tank experiment 2 seconds after vibration started. The crests of the water ripples are presented by the dark lines. Given this information, what is represented at P at this instant? And what is the frequency of the vibrator? Please pause the video and try this yourself. Looking at the figure, we can see that P is between 2 crests. Therefore, P is represented as a throw. The frequency of the vibrator can be given as 4/2, which is 2 Hz. Next question. 2 dot vibrators, which has a separation of 5 centimeters, are placed on a water surface in a ripple tank. The distance between 2 adjacent antinodes on a screen is 10 centimeters. What is the wavelength of the water wave? Please pause the video and try it yourself. The wavelength is equal to 5 times 3 over 10, which gives us 1.5 centimeters. Moving on to the next question. The wavelength of light can be determined with a double slit plate. The diagram above shows the pattern of interference fringes obtained in a Young's double slit experiment. The separation distance of the 2 slits is 0.2 millimeters, and the distance between the screen and the double slit plate is 4 meters. Calculate the wavelength of the light used in the experiment. Please pause the video and try it yourself. To find lambda, we first need to know the values of x, a, and d. We know that 6x is equal to 14 millimeters, which gives us x is equal to 2 millimeters. We already know that d is equal to 4 meters, and a is equal to 0.2 millimeters. Plugging this into the equation that we know, we have that lambda is equal to 1 times 10 to the negative 7 meters. Sound waves. Sound waves are produced by vibrations. The vibrations cause compressions and rarefactions of air molecules. Sound waves need a medium to travel. We cannot hear any sounds in a vacuum. Loudness and pitch of sound waves. Figure 1.33 shows the graph of loudness. To decrease loudness, the amplitude should be reduced, while increasing the amplitude will raise the loudness. Figure 1.34 shows the graph of the pitch of the sound waves. To reduce the pitch, the wavelength of the sound wave should be increased, while reducing the wavelength will increase the pitch. The sound wave equation. To determine the time taken for the sound waves to reflect, T is equal to 2D over V, where D is the distance between the speaker and the wall and V is the velocity of the sound wave. Applications of sound waves. Sound waves can be used in ultrasound scanning. Ultrasound is used for the scanning of fetuses in mothers' wombs. Sound waves can also be used in sonar. This is used to determine the depth of the sea. Sound waves can also be used to disintegrate kidney stones. High-intensity ultrasound waves is used to break kidney stones in patients' bodies. Based on the lesson we've learned so far, let's try to answer the next question. In an expedition to determine the depth of a freshwater lake using an ultrasonic ruler, a pulse of ultrasonic sound is generated and traveled to the bottom of the lake and is reflected back. The time taken by the pulse to travel to the bottom of the lake and return to the ruler is 0.35 seconds. If the speed of the sound in a freshwater lake is 1,482 meters per second, calculate the depth of the lake. Please pause the video and try it yourself. Using the equation that we learned before, 2D is equal to V times T, we know that D is equal to 1,482 meters per second multiplied by 0.35 seconds divided by 2, which is equal to 259.35 meters. Moving on to the next question. Figure 1 shows the use of sonar equipment to measure the depth of the sea. State the phenomena of sound waves applied in sonar equipment. Knowing that the sound wave of frequency of 6 times 10 to the 5 Hz are used to determine the depth of the sea, what is the wavelength of the sound wave in seawater? If the time traveled between the instant of the sound wave is sent to the instant the echo is received is 1.5 seconds, what is the depth of the sea? Please pause the video and try it yourself. The phenomena of the sound wave applied in sonar equipment is called reflection. To find lambda, we divide V by F, which is 1,500 divided by 6 times 10 to the 5, which is 2.5 times 10 to the negative 3 meters. To find D, we use D is equal to Vt over 2, which is 1,500 multiplied by 1.5 divided by 2, which gives us 1,125 meters. Let's move on to the next question. A ping pong ball is held with a string and placed near a loudspeaker as shown in figure 2. The loudspeaker emits a low frequency sound and the ping pong ball seems to vibrate to it. Explain how the sound from the loudspeaker produces a vibration on the ping pong ball. What will happen to the vibration of the ping pong ball if the loudness emits a louder sound or a sound with a higher pitch? If the frequency of the sound is 5 Hz, calculate the wavelength of the sound produced. Assume the speed of the sound in air is 350 meters per second. Please pause the video and try it yourself. The vibration of the loudspeaker moves the air molecules around it. The sound waves produced by the loudspeaker transfers the energy to the ping pong ball and causes it to move. When the volume of the speaker is increased, the ping pong ball will vibrate with a greater amplitude. When the frequency of the speaker increases, the ping pong ball will vibrate with a higher frequency. To find lambda, we use lambda is equal to v over f, which is 350 divided by 50, which gives us 7 meters. Electromagnetic waves. The full range of electromagnetic waves, arranged orderly in their wavelengths and frequencies, is called the electromagnetic spectrum. The figure above shows the full electromagnetic spectrum. As you can see, the colors that we see in daily life only make up for a very small segment of the electromagnetic spectrum. This is called the visible spectrum. Electromagnetic waves is produced by the electric and magnetic fields that oscillate at right angles to the direction of travel and at right angles to each other. This figure shows that electromagnetic waves have different uses based on their wavelengths. From longest to shortest wavelengths, we have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each of these waves have different uses, as seen in this figure. This concludes the wave lesson. Thank you for listening, and I'm looking forward to an awesome year with all of you.